Water electrolysis is nowadays probably one really promising possibility to produce hydrogen in a quite green way. So basically the water electrolysis represents the capability, by exploiting the use of a current, to break down and split the water in gaseous molecular hydrogen and gaseous molecular oxygen. So from a practice point of view, these types of reaction, at the very beginning it was produced, developed in a specific cell, in an electrolytic cell, that is known as Hofmann voltmeter. So an Hofmann voltmeter is basically a sort of cell in which we are introducing water, and due to the use of two inert materials electrode, often platinum, we can provide a potential difference from the negative pole to the positive one in order to promote these reactions and produce here bubbles of hydrogen in the gas phase, and here bubbles of oxygen in the gas phase. Obviously, since we know very well, in according with Avogadro principle, that basically same volume of gas contain the same moles, we can say that since here 2 moles of hydrogens are produced with respect to 1 mole of oxygen, this is just a stoichiometric balance, we are creating twice the volume of hydrogen with respect to the volume of oxygen. So we are producing more volume of hydrogen. This is quite simple. So obviously this is an electrolytic process, because this reaction is not spontaneous, and we need to provide a certain voltage in order to promote it. And the voltage that we need to provide is obviously quite simple, and is the voltage concerning the difference between the associated semi-reaction of hydrogen reduction and associated semi-reactions of oxygen oxidation. So basically here we have at the negative pole the cathode, because this is an electrolytic cell. So at the negative pole we have the cathode. Obviously this type of cell taking names of Hofmann voltmeter. This is the structure, the Hofmann voltmeter, and the semi-reactions involved are respectively the reductions of hydrogen. On the negative pole we have a reduction, so we are acting as a cathode, and it's due to the fact that this is an electrolytic cell. We are looking for an electrolyzer, and so we have H plus 1 electrons. It's able to give 1/2 gaseous hydrogen. So basically the current is able to break down water in H plus and OH minus at the very beginnings, leading to the formation with the use of an external circuit of this species and this species. Here we have OH for OH minus, it's gas, plus it's gas, is oxidized in order to give 4 electrons plus 2 times water plus oxygen. Obviously we need to balance the electrode, multiplying this 4 times of subdividing this 4. So basically we have something acting as a cathode and something acting as an anode, and the total potential difference that should be applied in order to promote this reaction is higher than 1.23 volt, is higher than this. Why higher than this? Because if we remember, for instance, the reduction potential associated with this reaction and this reaction, this is 0 volts. Obviously it depends also on the pH conditions in which we're working. but and this is also equal to 1.23. Obviously, in this case, in standard condition, because if you are moving away from the standard condition, obviously this decrease and this decrease too. But this is in accordance with what we have described, speaking about the Purbe diagram. Even if this potential is decreasing due to the pH, this potential is decreased with the same amount, and so the distance in terms of potential will remain the same always. And so the distance between this line, the line of hydrogen reduction, and the line of oxygen reduction is always 1.23 volts. And this is the zone of water stability. Rather than this is the zone of hydrogen and this is the zone of oxygen. What does it mean? That if we want to split water, we need to provide a potential difference that is enough in order to promote these reactions and this reaction. And so it should be higher with respect to this difference, 1.23, in order to ask from the stability zone of water and promote hydrogen's evolutions and oxygen evolution. We need to provide at least a potential difference higher with respect to this difference, the one defining the stability zone of water. But obviously this is just from a theoretical point of view, in open circuit conditions, because in the reality we know how much important is the rule of overtension, and for the reason this delta V it should be higher than 1.23. 1.23 is the limit value imagined to be in open circuit condition. But since we are in the reality, we have loss of energy, we need to provide an higher voltage. And now one extremely important aspect concerning the water electrolysis is that we are yes able to promote this and this can be collected as in order to provide energy. It's important to say also that often we have a membrane that can separate these two compartments in order to avoid the reaction between oxygens and the hydrogen in a sort of detonant mixture that can release energy. It could be dangerous, for instance. So what is important now is the rule of the electrolyte. But what does it mean, the rule of the electrolyte? In this electrolytic sense, it seems that no electrolyte is present, but this is a mistake. Because even if we are able to break down water in hydrogen and oxygen only by exploiting the current in order to close the circuit, because this is basically actually a real cell, is an electrolytic cell, but is a cell, we need to close the circuit. So we need to have a huge conductivity also inside this medium, inside water. But water has not sufficient conductivity in order to close the circuit and ensure a good electrolysis process. And so we need to introduce something that is a soluble water species that is able to act as electrolyte in order to improve the conductivity. And so we need to define what is the choice of this species. But what is important to say is that the electrolyte use, it cannot be random chosen. Because basically if you're choosing the bad types of soluble species with the bad types of released cations and released anions in solution, we're introducing maybe some species that can act versus the generation of hydrogen and oxygen. We can have a competition between the generations of hydrogen and the generations of oxygen. What does it mean? If you are remembering again the Purbe diagram, in which we have the line of oxygen, we have the line of hydrogen, and so here we have the stability zone of water, the stability zone of hydrogen, and the stability zone of oxygen, with the two connected semi-reactions for the hydrolysis of water. So this is the hydrolysis of water, and these are the connected semi-reaction. So H plus electrons to give this, and this is connected with a potential that, for instance, in standard conditions is 0 volts, and this is connected to a potential that in standard condition is 1.23 volts, and the difference is still maintained. If we are now introducing an electrolyte, if this electrolyte, for instance, it's characterized as a salt AB that release 1 protons and 1 not 1 protons, but 1 cations and 1 anion, something like this, for instance. If these anions, for instance, is characterized with a reduction potential that is maybe lower with respect to one of oxygen, maybe something like this, or something like this, it doesn't matter. So what is happening is that these types of anions, since it has a smaller potential, a smaller standard potentials, for instance, with respect to oxygen, is more easily oxidized, and it will be oxidized with respect to this one. And so we are not able to appreciate oxygen evolution, because all the electrons released from these reactions are collected from this one in order to be oxidized. Why? Because the difference between these two reactions is smaller with respect to this one. So we have a huge tendency to be oxidized of this species with respect to the oxygen. And so if we are choosing a wrong salts in order to increase the conductivity, we can have the oxidations of this species with respect to oxygen, with respect to OH minus, OH minus. And so we are basically missing the opportunity to create oxygen. And the same for what concerns the protons, because if the protons is characterized with a reduction potential, for instance, that is higher with respect to this one, is maybe 0.1, so it's higher, this means that this species is preferred to be reduced. It's preferred to be reduced, is a stronger oxidant. And this means that the reactions involve the reductions of this species in the moment in which we are applying current with respect to the reductions of this species. And so what does it mean? That if we want to improve the conductivity of water in order to close the circuit allowing the electrolysis, we need to introduce a salt characterized with a proton that is associated with a smaller reduction potential with respect to this one, and an anion associated with a higher reduction potential with respect to those of this redox couple. And so, for instance, the best types of cations that can be used are sodium and lithium. We know how low are the reductions potentials of sodiums and lithiums, and so are really, really low, and we are not fighting in any way the reductions of hydrogen. Or maybe we can even use an acid species, because if we introduce H+, we're not basically changing nothing, we're introducing the same species, and so no competition is present. This for what concerns, for instance, the cations, and for what concerns the anions, often the use of these anions is the best. The sulfate, actually the reactions of sulfuric acid is one of the best choice. Why? Because this species is associated with a huge reduction potential, higher with respect to this one, and so we are here, and we have no competition due to the generation of oxygen, because the gap of this salt species is huge with respect to the gap of water, and in the moment in which we are applying water, we are promoting this reduction and this oxidation. Since this reduction is favor and this oxidation is favor with respect to this one and with respect to this one. So basically, if we want to define better the civil reactions involved due to the presence of an acid, well, we can say that if we are using an acid, so this is H+, this reaction is still the same, whereas if we are using sulfuric acid, we have, for instance, this reaction, the oxidations of this species, that is equal to the oxidations of this species that is associated with a standard potential 2.01. So it's really higher with respect to this one. So we have no competition mechanisms. Since this is tend to be oxidized smaller with respect to this one, we can say that this species is sort of something. It's obviously not a metal, so we cannot say that it's more noble but it's something similar. So basically, it's difficult to oxidize this species with respect to this one. So all the electrons released from these reductions are collected from this species and not from this one, since the reduction potential is smaller and the tendency to be oxidized is higher. In this case, since we are introduced sulfuric acid, we have H+, and no competition mechanisms. We can even use some, for instance, alkaline species, something like this, for instance, as electrolyte, but often these types of alkaline species are not used a lot, since it is better often to work in acid conditions, because it's true that working in acid conditions means to use more noble material as platinum as electrode, because we need to resist versus corrosion. But it's also true that if you're using, for instance, alkaline electrolyte together with hydrogen, we are producing close to this electrode the presence of some alkaline fogs that are difficult to be removed. Because if we are working in alkaline condition, this reaction is not these reactions anymore, but is this reaction. We have again the evolution of hydrogen, but we have the generations of alkaline fogs that can be difficult to be removed, with an associated standard potential that is equal to minus 0.83 volt. So in general, in order to avoid the formations of this species close to the negative electrode when we are creating hydrogen, it's better to work in acid conditions. In acid conditions, since the protons cannot affect these reactions in any way, and the presence of these anions sulfuric acid is associated with a tendency to be oxidized smaller with respect to this one, and so we have no competitions in the electrolysis of water process.